Okay, we have covered the singularity decomposition and pseudo inverse and the least square solutions. Okay, I think that's about the end of the theory that we have deeply studied. And now we're going to start from the start. But now we start with the complex eigenvalues and complex eigenvectors. So far, we only have treated the matrices whose eigenvalues are real. Okay? So matrices are real matrices and eigenvalues are real eigenvalues. Then eigenvectors should be real vectors, isn't it? But some real matrices can have complex eigenvalues. Okay? In that case, the eigenvectors should include the complex numbers in it. Okay? We're going to cover that case. First, we define the set of complex vectors, n-dimensional set of n-dimensional complex vectors. Let's say Cn instead of Rn for real. And then these EIs and E2Cn, these are called the standard basis for Cn. Okay? So any vectors in Cn can be written as a linear combination of these standard bases, EIs. Okay? Here, these GIs are complex numbers instead of real. Okay? And for the complex number, G is equal to A plus BI, G bar is a conjugate. So it should be A minus BI. And the absolute value of G is defined as a square root of A square plus B square, which are real numbers. A and B are real numbers. And G is a complex number. We call it is a modulus of the complex number G. And this complex number can be written as R is equal to cosine theta plus I sin theta. This equation is called the Euler's equation. And the R is equal to the modulus of the complex number G, and the tangent theta is equal to B over A. This is what you have learned in the high school years. Okay. And we now define the Euclidean inner product. Suppose we have two complex vectors in Cn, then inner product of those U and V can be defined in this way. Like instead of just U1, V1, we write V1 conjugate times U1 plus V2 conjugate times U2 and Vn conjugate times Un. This is the proper way to define the inner product for the complex numbers. I will explain why this is a better way of defining the complex numbers. This is actually same as V star, which is a 1 by n matrix, times U, which is n by 1 matrix, gives us 1 by 1 scalar complex number. Okay, if this operation satisfies these four properties, all other properties same with the inner product for the real vectors. The only difference is the first one. It's not symmetric, but it's symmetric with the conjugate, like this. Okay. If this operation, this operation satisfies this four property, then we call this is an inner product. Particularly Euclidean inner product for Cn. The norm is defined like what we did before for real Rn, except those we are using the modulus. Yeah. And distance is defined similarly as what we did for the real vectors. And angle and orthogonality are defined similarly. You can compute the inner product and distance with the given definitions without difficulties. These are the code to find finding the inner product of the given matrix and the norm of the given two matrices, and the distance between two given vectors. Okay. As you see, those answers are exactly same as what we did find by hand. This scheme. So you have tried this. You can find it. But it's for the real number, you can easily compute it. But the complex, if the size is big, then it's just tedious. And so, but the interesting thing is the code are almost the same as what we did for real. The simple code gives the same answer without the tedious computations. So when you know the code, it's much easier to deal with the complex problems, complicated mathematical problems. When you deal with the easy, simple problems, you can handle it by your hand. The code could be difficult, but when the problem is getting complicated, code is the same, but it handles very well. So that's why now you need ability to think the algorithmically, and that's why you need a computational thinking at this point. You now have a computational abilities, so you should think. You should use those abilities. So you need to be equipped with the ability to think computationally. So computational thinking is needed to communicate with those computational tools which is utilized for you now in this 21st century for free, almost. Mr. Lee, do you agree? Yes. Complex eigenvalues and eigenvectors of real matrix. Okay. Suppose we have a real square matrix of order n, but still it can have a complex eigenvalues. If lambda is a complex eigenvalue of n by n real matrix A, then and x is the corresponding eigenvector, then complex conjugate, lambda conjugate of lambda is also an eigenvalue of A, and x conjugate is also an eigenvector corresponding to lambda conjugate. Because of this, if Ax is equal to lambda x, and x is an eigenvector, then, and x is real, then as you see, A conjugate is same as A, isn't it? So if you take a conjugate like this, Ax and Ax conjugate should be same as lambda x conjugate, which can be written as this, and which can be, left-hand side can be written as the real matrix A times x conjugate, which means this lambda conjugate is an eigenvalue of x, of A, and this x conjugate is a corresponding eigenvector. Okay? So if you have a real matrix, if lambda is an eigenvalue, then its conjugate is also an eigenvalue. So this is a very interesting fact. Next. If A is equal to A conjugate transpose, then all eigenvalues of A are real numbers. The complex conjugate transpose is written as A star. We just simply write A star instead of conjugate transpose. So if A is equal to A star, then all eigenvalues are real numbers. The proof is this simple. The proof that you have seen in chapter 7 was much more complicated for the real matrix. But the complex matrix, this proof is much simpler, as you see here. Here, if lambda is an eigenvalue of A, then there exists a non-zero vector x such that Ax equals to lambda x. Okay? And we multiply x star, which is a conjugate transpose on both sides. On the left-hand side, then x star Ax should be same as x star lambda x. And lambda is a scalar, so scalar can come out. So x star x is a inner product of an x and x, which is same as the square of norm of x. Okay? So lambda can be written as this, x star Ax over the square of x norm of x. And x was an eigenvector, which is non-zero. So this denominator is not zero. So this lambda is defined. this is a non-zero real number, so we just need to show x star ax is a real number. So if x star ax is a real number, then lambda should be a real number, isn't it? Okay. So because this is a real number, x star. So what you have to show is if the conjugate of x star ax is same as x star ax, that means x star ax is a real number, and lambda, which is an eigenvalue, is a real number. So that means all eigenvalues of A are real numbers. So start from here. Then we can rewrite it in this way. Here, this can be written as this 1 by 1 matrix. So 1 by 1 matrix is same as its transpose, isn't it? 1 by 1 real number is same as its transpose. So this can be written as this. Clear, isn't it? So this can be written as, because it's a scalar, this can be written as transpose of A x conjugate times x, like this. This can be split it like this, and this can be written in this way. Here, x conjugate transpose is x star, and A conjugate transpose is A. So this is just same as x star ax, which is same as conjugate of it, which means this is a real number. This is because A is equal to A star. A star is equal to A. So this is a real number. So lambda is a real number, which means all eigenvalues of such a matrix are real numbers. That's very important. Real eigenvalues. Okay, here is some examples which has complex eigenvalues and how it shows. Okay, I think here, this is the end of this section. Albert Einstein told that pure mathematics is the poetry of logical ideas. That's what you are learning in this math class. Next, Hermitian matrix and unitary matrix and normal matrices. Complex conjugate transpose. Yeah, the X conjugate, and this is the conjugate transpose. This is called the conjugate transpose of A. We call it is A star. So A star is conjugate transpose. Yeah, we define already. Here, like this, inner product, Euclidean inner product, the complex number, complex vector U and V, is just this, V star U. If U and V are n by 1 vectors, then V star is 1 by n vector, and U is a n by 1 vector, so the product is 1 by 1 scalar. Okay? So, and the norm is this. This is what we defined already. Okay? So this is a note. Suppose you have A, B, C, then A star can be defined in this way, and B star can be defined in this way. C star is 1, 3, 2, 4. And this is a real number, so conjugate doesn't affect. This is a property of conjugate transpose. Conjugate transpose, like this. And Hermitian matrix. So the next, it's almost similar like what you had on the transpose, isn't it? Star is itself. And AB star, AB transpose is equal to B transpose times A transpose, isn't it? It's a similar. This is a generalization of the property of the transpose of a given matrix. So see, this is complex matrix version of the transpose. Okay, this the special matrix which satisfies this condition. If A is equal to A star, if A is same as a conjugate transpose, then we call it a Hermitian matrix. Hermitian matrix. This also. Yeah. This is a property of Hermitian matrices. If A is a Hermitian matrix, X star AX is always a real number for any vector X. And eigenvalues of Hermitian matrices are all real. And eigenvectors of A corresponding to distinct eigenvalues are all orthogonal to each other. This is very important. If Theorem 8.7.2 shows if A is equal to A star, then every eigenvalues are real numbers. So the second part is just the same as theorem 8.7.2. Okay. The new things is this one. Corresponding eigenvectors are orthogonals. What is this? When you had a symmetric matrix is all eigenvalues are real, and it was unitarily diagonalizable, orthogonally diagonalizable. So this Hermitian matrix is something like, it's a general version of the orthogonal diagonalization, orthogonally diagonalizable matrix. So we're going to study that. The complex version is unitary diagonalizable matrix. This Hermitian matrix is unitary diagonalizable matrix. Okay. Okay, this matrix is equal to A star. Yeah, here we find the eigenvalues, and we can find the eigenvectors. As you see here, these eigenvectors are orthogonal. And skew Hermitian, if A equal to minus A star, then we call it a skew Hermitian, like a skew symmetric matrix. With this, every matrix can be written as the sum of Hermitian part of the matrix and skew Hermitian part of the matrix, like what we did see for the skew symmetric matrix and symmetric matrix. This is, so everything that you have learned for the real matrix are generalized in the complex matrix setting. And here we define a unitary matrix, which is U star U is equal to identity, like A transpose A is equal to identity. For when A is a real matrix and A transpose A is equal to identity matrix, then we call that matrix is a real orthogonal matrix. Now, if U star U is equal to identity matrix, then we call this U matrix is a unitary matrix, which means the inner product of the columns of the unitary matrix U are all zero if they are different, and if I is equal to J, then it is equal to 1. So, which means the column vectors of the matrix U are also normal vectors. Okay? So, if U is a unitary matrix, and if and only if the columns of the U forms an also normal set in Cn. Okay, so this is an example of the unitary matrix. A star is equal to identity matrix. You can easily find this. You can easily check it, because even for the large size matrix, you have a code. You can define a matrix, Mohammed, isn't it? You can define the transpose of the given matrix, A. You can find the conjugate transpose of it. Then you can multiply this A star A easily, isn't it? So you can find, we can check whether the result is an identity matrix or not for any matrix. So if I give you any complex matrix, you can check whether the matrix is unitary or not with a simple 3-4 line code, isn't it? This is a property of a unitary matrix. If it's a unitary matrix, the norm of Ux is same as norm of X. What this means is U is a linear transformation. Send X to Ux in the codomain. But length of X is same as length of Ux. So when you have a linear transformation, when you have a function, the distance of the original one, the same as this distance, the norm, the magnitude of the image. This is very important fact. The size in the domain is same as the image. It's amazing, very important fact. Next, if lambda is an eigenvalue, then its modulus, the magnitude, is equal to just 1. All the eigenvalues are on the unit circle. And eigenvectors of U correspond to the distinct eigenvalues are orthogonal to each other, like what you did see before. Okay, eigenvectors are orthogonal for the unitary matrix. This property is called the isometry, or preserving the norm. The norm in the domain is same as norm in the codomain. Okay. So we call it isometry. Metric distance is iso, same. So it's distance preserving, norm preserving mappings. So unitary matrix is a linear transformation that preserves the norm, length, distance. Okay. This is definition. Unitarily similar and unitarily diagonalizable. If AB are n by n matrix, complex matrix, and there exists a unitary matrix U such that U star AU is equal to V, then A and B are called unitarily similar to each other. Unitarily similar. If A is unitarily similar to any diagonal matrix, then we call A is unitarily diagonalizable. So U star AU is equal to a diagonal matrix, which is nice. Okay? If a matrix is unitarily diagonalizable, you can change the complex matrix to a diagonal matrix by using a unitary matrix, which has a wonderful properties. Okay? This is an example. If A is this U is equal to like this, then U star AU can be written in this way, which is a diagonal matrix, whose main diagonal entries are 3 and 1s. Isn't it nice? A is a complex matrix, but this similar diagonal matrix is just 3, 0, 0, 1, which is very easy to handle, isn't it? You don't even need to use code for the complex matrices. Miss Kim, G1, if this matrix A is unitarily diagonalizable, then all the computation you do can be done in here, in this diagonal matrix, instead of A. But this is a real matrix and diagonal matrix. So the computation from now only can be done in the real field, which you already finished. So you don't even worry about the CDF or CC. You just do everything in the real. Okay? Mm-hmm. So this unitary diagonalizable means a lot. You don't have to use the code for real and complex and mixed up. You only use the code that we have used so far. That's enough if the matrix is unitarily diagonalizable. Okay? And like this. If A is unitary diagonalizable, then there is a unitary matrix U such that U star A is equal to D. Okay? D. And the diagonal entries of these are eigenvalues of the matrix, as you see. Hence, if you multiply U on both sides, then you have AU is equal to UD, which when U has the column vectors like this, then AU can be written in this way and UD can be written in this way, which means AU1 is same as lambda 1 U1. The first columns are same, which means lambda 1 is the eigenvalue of A, and this U to the 1 is the corresponding eigenvectors. And this AUN is the same as lambda n UN, which means lambda n is an eigenvalue, and UN is its corresponding eigenvectors. So UIs, this unitary matrix, the columns of unitary matrix U are the corresponding eigenvectors. So when you have U star AU is equal to D, you already have all the eigenvalues in the diagonal matrix and all also normal eigenvectors in the matrix U. Got it? Miss No? If U star AU is equal to D, if you can find it, that means you have all the eigenvalues here and you have all and also normal eigenvectors. So you don't even need the Gram-Schmidt also normalization process to find also normal eigenvectors. Got it? So this is nice. So so this is the end of chapter 7 and 8, isn't it? So you already have real eigenvalues and you have eigenvalues and you have also normal eigenvectors and also normal eigenvectors. So you can do, that means you have a very simplified problem that you can handle easily. Got it? Mm-hmm. Miss Kim, G1. Got it? So if you have a unitary diagonalizable matrix, then everything's easy. with the knowledge that you have learned so far. Problem has been simplified to a diagonal matrix. Yeah. You are on the highway of all the computations and all the analysis of the situation with this unitary diagonalizable matrix. Okay? Suppose you have a matrix A like this, then you can find the unitary matrix that diagonalizing this matrix A. Here, all you have to do is find the eigenvalues and find the corresponding eigenvectors and normalize it. Then you have the matrix U, whose column vectors are normalized eigenvectors, and the diagonal matrix whose diagonal entries are eigenvalues lambda 1 and lambda 2. Done. For any matrix here, you can find the eigenvalues. And you can find the eigenvectors. And you can normalize it. So you can have the column vectors of U. Then you have matrix U and D, which makes U star AU is equal to D, which means A is unitarily diagonalizable. Done. This is the last theorem, Schur's theorem. The thing is, if every matrix is unitarily diagonalizable, then it's good. It's good. But not every matrix is unitarily diagonalizable. If it's a Hermitian matrix, then it is unitarily diagonalizable. But if it's not Hermitian, you cannot say it is unitarily diagonalizable. But the mathematician Schur proved this theorem, which says A square matrix A is unitarily similar to an upper triangular matrix. May not be a diagonal matrix, but unitarily similar to an upper triangular matrix whose main diagonal entries are the eigenvalues of A. So like this, there exists a unitary matrix U such that U star AU is equal to an upper triangular matrix T, whose main diagonal entries are eigenvalues of A. This is good enough. We have an upper triangular matrix T for arbitrary matrix, not only Hermitian matrix. For any matrix, you can simplify by using the A unitary matrix that makes U star AU is equal to triangular matrix T, whose main diagonal entries are eigenvalues of A. This is possible because of this proof. If lambda I is an eigenvalues of A, okay, then we use mathematical induction to prove this. Okay, so when n is equal to 1, it's a 1-by-1 matrix. Then you have the A11 entry is itself an eigenvalue lambda 1, and so it is a triangular matrix. So it is true. Now assume true. The statement is true for any square matrix of order less than or equal to n minus 1. So with this the assumption, induction assumption, that we start with the x1, which is an eigenvector corresponding to eigenvalue lambda 1. Then by the Gram-Schmidt orthonormalization process, we can find an orthonormal basis for Cn, including x1. So we say it is S, which starts from x1 to with the GIs. Since S is also normal, the matrix U, whose column vectors are this vector x1 and g2 and gn, is a unitary matrix. If you think about U0 star AU0, then it can be written in this way. Because AX1 is equal to lambda 1 x1. Lambda 1 is an eigenvalue, and x1 is its corresponding eigenvectors. And the first column of AU0 is lambda 1 x1. So since the UIs are also normal vectors, so all the entries below this lambda 1s are zeros. So U0 star AU0 can be written in this way. This lambda 1 and stars are here, and zero vectors here, and the submatrix A1 here. Okay, now this A1 is an n minus 1 by n minus 1 matrix. So now we can use a mass induction. And also the characteristic polynomial of A now can be written as this because of this. So lambda 1 factored it out. So all the other eigenvalues from lambda 2 to lambda n should be eigenvalues of the submatrix A1. So the A1 has these eigenvalues as lambda 2 to lambda n minus 1 eigenvalues. Now we use mass induction on this matrix A1, whose eigenvalues are this. So by the mass induction hypothesis, there exists a unitary matrix U1 hat, which has U1 hat star times A1 times U1 hat is equal to a triangular matrix, upper triangular matrix whose main diagonal entries are eigenvalues lambda 2 to lambda n. So if you define the U1, which is a n by n matrix, which is this, including the submatrix U1 hat, then if you multiply the star of U0 U1 times A times U0 U1 is equal to this, which can be written as this, which is a upper triangular matrix whose main diagonal entries are all eigenvalues of A. So the Schur's theorem has been proved because this matrix product U0 U1 is a unitary matrix because it's a product of two unitary matrices. So itself is a unitary matrix. So Schur's theorem has been proved. That's it. That's it. So now with this theorem, which was proved by Isaiah Schur, so whenever you have any matrix, you can just find the unitarily similar the upper triangular matrix, and then you can start with that upper triangular matrix whose main diagonal entries are eigenvalues. That's the contribution of Isaiah Schur. Normal matrix. If A star is equal to A star A, then we call this matrix is a normal matrix. Okay, this matrix A and B's are normal matrices. An equivalent condition for a matrix to be a normal here. The following are equivalent for n by n matrix A. A is unitary diagonalizable, which we like to have. This is a property that we like to have. Second, A is a normal matrix. They are if and only if. And if and only if A has n also normal eigenvectors. These are the equivalent conditions. So if you want to have a unitary diagonalizable matrix, then all you have to do is just find what? A star. And multiply A star on A. And compute, then check whether A star A is equal to A star. You can easily check. If they are same, then you can say it is unitary diagonalizable. Then you can think what? Just diagonal matrix. Okay? Done. And it has n also normal eigenvectors, which is the column vectors of that unitary matrix U. Okay? That's it. So this is checking whether it is a normal matrix or not is very easy, but it is powerful. Now you have a unitarily diagonalizable matrix. So you have also normal vectors and the diagonal matrix whose main diagonal entries are eigenvalues of A. Okay, this is an example, matrix A and U. And here, it is, as you see here, this shows this A matrix is a normal matrix. So it is a unitary diagonalizable. So if you find eigenvalues and its corresponding eigenvectors, then it is going to be a orthonormal eigenvectors that you are looking for. So after you check the given matrix is a normal matrix, everything's easy. You just find the eigenvalues and eigenvectors. And you know those eigenvectors are also gonal. So you can just normalize it to find the matrix U. This matrix is unitary diagonalizable because it is Hermitian. It is Hermitian. It's a Hermitian. If Hermitian is A is equal to A star, then clearly A star is same as A star A because A star is A. So Hermitian, if a matrix is a Hermitian matrix, then it is a normal matrix. Okay? So it is unitary diagonalizable. Okay, I think this is the end of chapter 8. Although not every matrix A is diagonalizable, using the Schur theorem, we can obtain an upper triangular matrix JA, which is similar to A. This upper triangular matrix JA is called the Jordan canonical form that we will study in chapter 10. Okay, the next section is the linear system of differential equation that Mohammed should know. This is this is differential equation that you learned in engineering mathematics. Okay, here I may just show you some. Okay, allow it. Then this is a part of differential equation, but your knowledge of linear algebra can be used for the differential equation like this, system of differential equation like this. Okay, for example, if you have a differential equation like this, then this can be written as this matrix form like this with these vectors. Then this can be written as x prime is equal to ax with the matrix A. Here, the solution of this differential equation, solution of these differential equations can be found in this way. But if you use the matrix, then this is the knowledge of matrix. Then here, these differential equations can be solved by this linear system of equation and finding the eigenvalues and its corresponding eigenvectors. And this is why we have learned the matrix linear algebra. Here, the differential equation can be written as a system of linear system of the equations. The high order linear differential equation can be written as a system of linear equations, which can be written in this form. This is equivalent. This the higher degree differential equation can be written as a linear system of differential equation, which can be written as this matrix form, x prime is equal to ax. Then the solution of this higher order differential equation can be found by using the eigenvalues and eigenvectors of this matrix, which is x prime is equal to ax. This is the whole idea. So you will see those in the course of differential equation or engineering mathematics. Okay. Okay. Angry Poincaré told that it is through science that we prove, but through intuition that we discover. I think that's the closing meant for chapter 8. Any questions? And yeah, you have already solved the many problems in chapter 8. Any questions? Mr. Lee?